For instance, we can use the same trick to obtain an antiderivative of arc sine x. So we're going to use integration by parts where we differentiate arc sine x and therefore integrate dx. du is then dx over root of 1 minus x squared, and v is x. So uv is x arc sine x, and v du is x over root of 1 minus x squared dx. Now in this integral, we can now use substitution because we have a composite part. We have 1 minus x squared plugged inside the square root function, or more precisely 1 over square root. And at the top we have x dx, which is a constant multiple of the derivative of what's inside the square root, because the derivative of 1 minus x squared is negative 2x. So we use the substitution w is 1 minus x squared, which gives us dw is negative 2x dx, or if you wish, x dx is negative 1/2 dw. So in this integral I'm going to replace x dx by negative 1/2 dw, and square root of 1 minus x squared by square root of u. So we obtain x arc sine x plus 1/2 integral of dw over root w. Well, 1 over 2 root w is the derivative of root w, in other words, an antiderivative of 1/2 an antiderivative of 1 over 2 square root of w is root of w. And w was 1 minus x squared. So we obtain x arc sine x plus root of 1 minus x squared up to a constant. A third example, where we can try to use the same trick of integration by parts to find an antiderivative, is arctangent x. Because we don't know an antiderivative, but we know the derivative, so we can try by parts differentiating arctangent x. So we take u is arctangent x, dv is dx, therefore du is the derivative, 1 over 1 plus x squared times dx, and v is x. uv is x arctangent x, and v du is x over 1 plus x squared dx. Now in this integral, we can use substitution, because what we have at the top, x, is a constant multiple of the derivative of the bottom, and 1 plus x squared has derivative 2x. So we use a substitution like that. W is 1 plus x squared, and so dw is 2x dx, or in other words, x dx is 1/2 dw. So we replace x dx by 1/2 dw, 1 plus x squared by w, and we obtain x arctangent x minus 1/2 integral of dw over w, whose antiderivative is natural log of absolute value of w. Because w was 1 plus x squared, it's in particular positive, and so we obtain x arctangent x minus 1/2 natural log of 1 plus x squared up to a constant. One last example that is of slightly different nature. We're trying to integrate t cubed e to the t. First we should see if there is an easy way to obtain this integral. We don't know the antiderivative right on top of the red, and there's no obvious substitution, so integration by parts is an option. First we need to pick what is going to be u, what is going to be dv. We use the same rule of thumb as usual, try to see what would be simplified. E to the t, whether we differentiate or integrate, we're going to still get e to the t, so the complexity is going to be the same. T cubed on the other hand, if we integrate we get t to the 4 over 4, if we differentiate we get 3t squared. It looks like we're better off by differentiating, so we're going to take for u t cubed, and for dv e to the t dt. Applying the integration by parts formula, we obtain uv, which is t cubed e to the t, minus integral of v du, that's e to the t times 3t squared dt, so we obtain minus 3 integral of t squared e to the t dt. So here the problem is that we changed the integral, alright, but in the previous cases, each time we used integration by parts, we transformed the integral into some function plus another integral, and that other integral was easy to calculate. But now we transformed it the same way, a function plus another integral, but it's still not clear what this integral is. We obtain integral of t squared e to the t, and it looks pretty much as difficult as the previous one. Not quite though, because we started with integral of a polynomial of degree 3 times e to the t, and now we have an integral of a polynomial of degree 2 times e to the t. If we use integration by parts on that again, the same way, differentiating t squared, we should expect to get an integral of a polynomial of degree 1 times e to the t. And doing it again, getting just integral of e to the t. So this is exactly what we're going to do, iterate this process. So I'm going to iterate this process and use integration by parts for the integral of t squared e to the t. Differentiating t squared, integrating e to the t. Derivative of u is 2t dt, and antiderivative of e to the t is e to the t. So we get t cubed e to the t minus 3 times what we obtain using the integration by parts formula on this second integral, namely uv, that's t squared e to the t, minus v du, that's 2 integral of t e to the t dt. So that simplifies as e to the t multiplied by t cubed minus 3t squared, plus 6 integral of t e to the t. Well, we're still not done, but as expected, we now have an integral of something of degree 1 times e to the t, so if we do it once more, we should get just a constant times e to the t. So we're going to again differentiate t, integrate e to the t. So we obtain dt for du and e to the t for v, and apply the integration by part formula for this integral. So we have the first term that is unchanged, e to the t times t cubed minus 3t squared, plus 6 times what we obtain applying the integration by parts formula, namely uv is t e to the t, integral of v du is just the integral of e to the t dt, but integral of e to the t is just e to the t. So we obtain 6t e to the t minus 6e to the t, and factoring e to the t, we obtain e to the t multiplied by t cubed minus 3t squared plus 6t minus 6, all this up to a constant. Now turn to the next video to see how we apply this integration by parts formula in the case of definite integrals.